from the Department of Civil, Environmental, and Geoengineering. My name is Joe Labus. I'm department head, and I have the privilege to introduce today's speaker. But first, I'd like to tell you a little bit about today's seminar, which is dedicated to Professor Jānis Vardalakis, a former faculty member in this department. So, Jānis received his undergraduate degree at NTU in Athens and went to Germany for his PhD, where he studied with Professor Gudehus. He spent a few years in Karlsruhe before coming to the University of Minnesota, where he advanced quickly through the ranks, where he was professor, and until he left in, I believe it was 1990 or 89. Jānis was very prolific in terms of writing, very well cited, and of course many of you may know him for his theoretical work, but he was quite proficient as an experimentalist. And I'd like to point out one of his major accomplishments in terms of the study of localization of deformation and the development of apparatus to study this type of phenomenon, which segues nicely into today's speaker, who is also noted for his work on localization. So Professor John Rudnicki is a faculty member at the University of Minnesota, at Northwestern University. We tried, but... Yeah. John received his degrees at Brown University. He did postdocs at Caltech and University of Illinois at Urbana-Champaign before joining the faculty at Northwestern. He's noted for his work in inelastic and elastic behavior of geomaterials, working in the areas of bifurcation theory, poroelasticity, and fracture mechanics. He's received a number of awards, the Bio Medal, the Prager Medal. He's on a number of committees, technical committees, editorial boards, and he is an outstanding instructor, and I think you'll see that in today's lecture. Certainly he's most noted for, he's done outstanding work throughout his career, but his PhD work is very highly cited. With that, I'd like you to join me in welcoming Professor Rudnicki.
Okay, thanks, Joe. It's always a pleasure to visit this department, so I'm happy to be here. I was a great admirer of Jānis Vardalakis' work. I didn't know him all that well, but I knew him well enough to appreciate his enthusiasm and creativity. And so I'm honored to be able to give this lecture. I know I follow a line of distinguished lectures here, so I'm happy to be here again. Okay, so the title of the talk is up there. And a number of people have been involved in this. They're listed there. I won't go through them. But I've highlighted Bill Olson's name because I think he made some seminal contributions that are underappreciated. And the work was supported by the Department of Energy. Okay, this is an outline of the talk. I'll explain what these localized compaction bands are, say a little bit about why they're important, show you many pictures of what they look like, both in the lab and in the field, give a simple model for why they might form, and then, if I have time, talk about a little bit about the models for propagation. So this is maybe a simple slide that people know. So the canonical rock mechanics experiment is to take a cylinder of rock. It's loaded on the sides by compressive stresses, not shown here, and then the axial stress is increased. And initially, it deforms relatively homogeneously. That's shown here. So the decrease between all the lines here is the same. But as you increase the axial stress, microcracks begin to localize, and eventually you form a through-going shear band or fault. And in low porosity rocks, typically this angle is like 55 to 65 degrees between the normal to the band and the axial direction. And in low porosity rocks, this formation of the band is typically associated with dilation, so increase of pore space, increase of pore space. If you go to more highly porous rocks, the band angle decreases, and formation of the band is accompanied by compaction, so decrease of pore space. And then in a limiting case, the band may actually form perpendicular to the most compressive stress. And this is I don't know, initially it might be a strange thing to see, but I'll show you that it's observed in experiments and give a simple model for why it's occurs. So why are these bands important? They're mainly important because the decrease in porosity is accompanied by a decrease in permeability. This is an example from a lab test. So this is permeability against axial strain. And as the axial strain increases, these bands begin to form and they decrease the permeability. Here you can see it's about 2 orders of magnitude. This is an example from the field. This is the host rock here. It has higher porosity. In the bands, porosity has been decreased. This is permeability. The decrease is about, again, an order of magnitude.
Could I ask a quick question of clarification?
Sure.
Is the term compaction band specifically when that angle decreases to 0?
Well, yeah, so there's 2 classes I'll say a little bit more about in the observations, but there's a pure compaction band, which is when the angle decreases to 0, and what they call a shear-enhanced compaction band, where the angle is low and compaction is accompanied by shear. Okay. So yeah, that's a good question that I should have made clearer. This is another example. So this is a CAT scan of material outside the band. The black is porosity. Inside the band, you can see the porosity is decreased. So this was converted to a numerical image, and then by finding things called the medial axes, which are kind of a structural idealization of the contact points, you can then construct flow paths, so shortest flow paths through these. This is inside the band and outside. So here you see there are many more flow paths than inside the band. These numbers are tortuosity. So the tortuosity is greater inside the band, so the wiggliness of the flow paths. And the permeability, again, decreases by about an order of magnitude. This is a cartoon, again, of why these are important. So if you have a reservoir where you're either extracting or injecting fluid and it's compacting relatively homogeneously, then there's flow to the wellhead or away from the wellhead if you're injecting. But if these bands form with decreases in permeability, then they can obstruct flow to the wellhead or out of the wellhead if you're injecting. Since these are very narrow, they're hard to detect from surface geophysical measurements. And so it's important to try and understand why they form, what kind of materials they form in, and what are the stress conditions in which they form. Okay, so that's kind of the overriding idea here. So what do they look like in the field? I'll show you many examples of these. So this is from the field work of Kurt Sternloff. It's located in southeastern Nevada near Las Vegas. And you can see all these little ridges. Okay, so these are compacting bands. So the porosity has been decreased there. They're re-cemented by subsequent processes. They're more resistant to erosion, and so they stand up relative to the host rock. And then I'll show another series of these. Here you see a number of them parallel. Here's a big one that sticks up, a big fin. You can see a depositional boundary here that crosses the fin with essentially no shear offset. So this is a pure compaction band. When other people started to look at this, oh no, here's a couple more. So this is again a long one that's relatively isolated. Kurt tried to look at relatively isolated ones for simplicity's sake. Let's see, what's the next one? So here's a micrograph of one of the bands. Again, pore space is blue here. It's much less inside the band. And again, you can see a depositional boundary here across which there's essentially no shear at the boundary. So again, this would be a pure compaction band. When
What are we looking at that we can't see shear across the boundary? So what can you point out in picture? You said you can tell this is a pure compaction band.
Yeah, so
How
if,
can I tell?
because this line, which is a depositional boundary, is not displaced parallel to these dashed lines.
And what do the dashed lines represent?
The dashed lines just make it easier to see the band. So the band is the region which has less porosity than outside. And pore space is blue here. Okay, and there's no shear displacement along here, so there's no displacement of this depositional boundary across the band boundary.
Is this quartz?
These are almost completely quartz sandstones, yeah, so 95 to 99% quartz sandstones, yes.
Thank you.
Okay. Yeah, so when people started to look at these in more detail, the situation got a bit more complicated. So there are pure compaction bands and shear enhanced compaction bands. Now you can't tell the difference by looking at this, and probably couldn't tell anyway if you're not a geologist. So this, we have to take geologist's word for this. But you can see that these are somewhat different. They're a little wavy, the pure compaction bands. The shear enhanced compaction bands are at a slightly different orientation. So one of the messages here is that, well, the morphology is slightly different, and they can occur in proximity. So they form under relatively similar stress states. Okay, another field example. This is from the work of Fossum, Schultz, and Tarabi in southern Utah. Okay, and again you see these are shear enhanced compaction bands, and here again you can't really distinguish them without the arrows, but you have pure compaction bands and these shear enhanced compaction bands, which are occur in close proximity. This is a thin section. So in this layer here, you see that the grains are much closer together. Blue again is pore space. And something to note is that the grains here are essentially uncracked. So I should have mentioned that in the earlier micrograph. You see very little or no grain cracking or crushing. Here's an example that addresses your question earlier. So here you see two bands, and they're offset here. So there was some shear across these bands. Okay. It's even more complicated. This is recent work of Peter Eichhubel and co-workers. So you can have bands in which you have essentially no grain fracturing, which is shown up here. But you can also have cataclastic bands in which you have a lot of grain fracturing and some grain crushing. On to laboratory experiments. Okay, so this is an example from the work of Bo, Klein, and Wong. So this again is an axisymmetric compression sample strain is increasing to the right, and these dark lines are the compaction bands. So they're initiated by the inhomogeneity of the end condition, then they progress into the sample, and as the axial strain gets larger, they progress further into the sample, and eventually the sample is covered with these bands. Let's see if I want to say, no, I don't want to say anything more about that. If you look at the bands in detail, here this is a band, so the grains are really crushed. And this is not, it's not really planar, so there's probably a fair amount of shear going on, although they're sort of labeled as compaction bands. This is a stress strain curve, two different confining stresses. You can see that there are little stress drops and then an increase, little stress drop. These are acoustic emission events that occur, and you get spikes where there's a little stress drop, and these are interpreted as indications of band formation in the sample. Now, it turns out that these kinds of bands are common in many other highly porous materials, and this is just one example for an open cell foam. So you see a similar phenomenology of small stress drops and then increases. In this case, the micromechanism is clear. When you buckle a cell wall, you have a little stress drop, and that causes a band to propagate across the sample. It gets denser, and so you transfer strain to the adjacent material and you form another band. Now, the strain here is enormous, 60%. Here we're talking a few percent strain. But it's interesting that if you look at the stress strain curves, they're not all that dissimilar. Inch down. I think this is my last example. So this is a axisymmetric compression sample instrumented by ultrasonic transducers. These will measure the acoustic emissions. Okay, and so this will take a minute to explain. So this is a stress strain curve. This one is axial stress versus strain. This is permeability decreasing to the left. And these are the location of acoustic emission events that occur during this red inchworm. Okay, if the movie works, you'll see this inchworm move up here. You'll see relatively random acoustic emissions till you get near the top. Then they'll localize near the ends of the specimen. And along this relatively flat portion, they'll propagate into the center of the specimen as kind of a kinematic wave. Let's see if this works. Yeah, so there they go. Okay, it goes fast. I'll show it again. So at the end, this turns up again, and you have relatively few events. Okay, one more time. Okay, so this, well, okay, skip that. Because this is, again, a micrograph. Here's the uncompacted material. Pink is pore space here, so there's a lot of pore space. This is the homogeneous compaction before that kinematic wave has passed. So you have a decrease in porosity, but relatively little or no grain fracturing. Once the band passes, you get quite a bit of grain fracturing. So a distinction between the lab and field data is you get a lot more crushing in the lab. Okay, and typically in the lab, stresses are much higher than people think were present in the field when these bands form. Okay, so a model that seems to give some indication of why these bands formed goes way back to actually my thesis work that Joe mentioned. And actually the idea goes well back before that, really to the first part of the last century. But the idea is that you have a chunk of material that's homogeneous and homogeneously deformed. So as you add an increment of strain or stress at the boundary, one possibility is that you have more homogeneous deformation. But we ask the question, when are the material properties and the stress conditions, when do they make it possible to have a second kind of deformation pattern, in particular one that corresponds to a narrow band, deformation localized in this narrow band. And typically, this is associated with decrease, softening of the stress strain curve. Let's see, how am I doing on time? Okay, so this is, it's a little small, but this is the mathematics of this. So there's a kinematic condition that the increment of displacement is a homogeneous part, so the part outside the band, plus a part that depends on only distance across the band. So this is a requirement that the increments themselves be continuous. That gives a strain increment of this form. You must have continuity of tractions across the band boundary by equilibrium. And then you need a constitutive relation, and here it's in the form of a rate-independent form that relates the stress increments to strain increments. If you put those things together, you get an equation that relates these G's, which describe the inhomogeneous part of the deformation increment, and they're driven by the homogeneous strain outside. Now, the simplest case is when this is zero. The band material and the outside the band material are the same. And you can show that that's the earliest bifurcation. So that's really the most basic kind of analysis. And then, since this is zero, you reduce to an eigenvalue problem, which if one possibility is the G's are zero, so then you don't get any band formation. And in order to have non-zero G's, the determinant of this must vanish. That places constraints on the orientation of the band and the kind of material properties that give rise to the band. So Giannis was also involved in quite a bit of analysis of this kind. Crucial ingredient is what kind of material behavior you put in there. And we use a rate-independent elastic plastic. This is shear stress against hydrostatic stress. This is the yield surface, which is the boundary of the elastic response. So for stress states in here, you get elastic response. If this were a metal, this yield surface would be a horizontal line. But in rocks, it's affected by the hydrostatic compression. In this portion, behavior is frictional. So the shear stress needed for yield increases with hydrostatic compression. And the response is dilatant. So if you plot the strain increment vector in this picture, it points to the left. Okay, so that corresponds to dilation. However, more porous rocks at a little bit higher compressive stresses, this begins to turn over and forms what they call a cap. And in this case, this strain increment vector points to the right, corresponding to compaction. Over here, the local slope, which is mu, is positive. Here it becomes negative. So let's see what else. Yeah, this is the increment of inelastic volume strain to inelastic shear strain, and that ratio is beta. So beta and mu will appear a lot in the next few slides. The main thing to note is that they're positive over here and they become negative over here. The other thing that comes out of this is that there's a condition on the stress-strain curve that the slope must be some less than some critical value in order for this band to form. And usually that critical value is negative. Okay, so you must have softening. Okay, when you go through that analysis, here's what you get for the band orientation. So this is, again, the angle between the normal to the band and the axial direction. So if beta plus mu over 2 are not too large or too small, you get orientations like this. It's bigger when you're dilating, and it's smaller when you're compacting. So that's agrees with the phenomenology. If beta and mu become sufficiently negative, then the only solution for this localized band is one which is perpendicular to the most compressive stress, which is the axial stress here. If beta and mu becomes sufficiently large, you actually predict a dilation band. People have claimed they've seen these. I'm a little skeptical that they're actually dilation bands. But this is the prediction of that analysis for the band angle. And this is just to remind you that that angle decreases when you go from dilation to compaction. So that's the prediction's consistent with that. Here's another picture. So this is the dilatancy angle defined in this way. So it's related to that beta. This range, these are band angles here. So this range is what Aikubal et al. Observed in the southeastern Nevada field site. And it must be dilation, so negative dilatancy angle. So the beta and mu's, well, I should have said that the plots, the lines here are values of beta minus mu, must be in this range. And this implies that beta is negative, so compaction, but mu is slightly positive. This is another complicated picture. So this is beta against mu. The blue lines are contours of that dilation, the dilatancy factor. The red are lines denoting the band angle. Okay, so this is again laboratory data from Wong et al. Falls into this range here. Okay, and that corresponds to band angles that are less than 45 degrees and dilation. Okay, here they also find mu positive and beta negative. So mu is slightly positive and beta negative. And just to go back to that picture, that suggests that these bands form sort of in this region here where the curve is turning over. So mu can actually be positive, but this vector points to the right, this compaction. Now this is also consistent with laboratory experiments which show that you tend to get band formation in this region, and called the cataclastic deformation region. You tend not to get band formation way down here. This is a more detailed calculation for an elliptic cap, so it'll be explained on the next slide. So why elliptic? Because laboratory data are reasonably well fit by ellipses. Okay. We can skip that. So here's a simple model. We only are looking at the one part of the ellipse, so not the yield surface back here. Semi-axes B and A, and the ratio of those can be inferred from laboratory experiments. Again, this is shear stress versus compressive strain, not compression stress. And the image of the axisymmetric compression test is you load in hydrostatic compression till you get up to the lateral confining stress, and you increase the axial stress, which goes off in a line with slope square root of 3. So at high compressive stress, high confining stress, you hit this yield surface down here. At lower ones, you hit it back here. Okay, again, you go through this analysis that I just outlined, and here's what you find. So in this region, if you have high lateral confining stress, you predict compaction bands formation. However, down here, this K critical is quite negative, so you need a lot of softening. And so you tend not to see bands down here so much. And K critical increases until you get to here. Okay, so this is the most favorable place for compaction bands. However, it's also at the transition where you start to get shear bands. Anything else? So this is also the place where the K critical for shear bands is also positive. Not positive, it's greatest. And if you look at this is that K critical, this is the band angle, and this is normalized confining stress. So at high confining stress, you get only a compaction band. And then you start to get shear and compaction, and the band angle goes up from 0. Okay, so you're like in 20 degrees here. This is at K critical. Now, out here, high confining stress, the only solution is a compaction band, pure compaction band. But here you can get a shear enhanced compaction band and a pure compaction band. And remember, in the field data, you saw pure compaction bands and shear enhanced compaction bands in close proximity. So this is, again, is in qualitative agreement with that here it's relatively the same conditions that produce both shear bands and pure compaction bands. Page down. Okay, and this is just a laboratory example of that. So this is increasing confining stress. At low confining stress, you tend to get these shear bands at high angles. As you move to higher confining stresses, that angle goes down and becomes almost 0. So you can compare this to the analysis, which predicts where you start to get compaction bands. It agrees qualitatively, but when you put numbers, not all that great. This is, again, a micrograph of sort of a compaction band, which is wiggly. So again, even though it's called a compaction band, there's probably a combination of shear and compaction here. And the grains are crushed inside. So again, that's a characteristic feature of laboratory experiments. Let's see if I wanted to say anything about it. Oh, and that's just another picture. Well, let me show this now. So again, this is a picture. You get these sort of elliptical yield surface. And where you start to see compaction bands is where this turns over a bit. Generally, you don't see them down here. Okay, here's one exception to that. The last time I was here, I gave a seminar, and Andrew Drescher had some concerns about this kind of point down here. And actually, Joe and Andrew got into a discussion in which I became a bystander for most of the rest of the talk. So another question is how the bands extend. This is sort of a preface to that. So this is a plot of the normalized thickness of the band against its half length. There's lots of scatter here. Okay, but you can roughly fit an ellipse through that. And I'll show in a second that the thickness is sort of a proxy for the compactive displacement. So this suggests a band-type model of an ellipsoidal inclusion. And that's sketched on this next slide. Okay, so this is my ellipsoidal inclusion. You can have some compactive displacement, which is given by this. Epsilon p is the inelastic volume strain. If it's small, it's roughly this. So this width W of the band is actually a proxy for the amount of compaction. And you can kind of see what is going to happen here if you have this ellipsoidal inclusion. Compaction is going to elevate the compressive stress at the edge of the band, and that's going to allow it to propagate. Now, since the material in the band was compacted and stiffer, I was convinced that this was really important, and I did a bunch of calculations with ellipsoidal bands and proved to myself that I was wrong, because the bands are so long and narrow in the field that what you have in here really doesn't matter all that much unless it's really, really stiff. Stiffer than would be reasonable given typical material properties. And that suggested that you could go to a model that was introduced by Fletcher and Pollard for a different kind of problem, pressure solution of an anti-crack model. So what is this? It's a tensile crack with all the signs reversed. Now, the crack, instead of opening, you predict interpenetration. However, that's interpreted physically as inelastic compaction of really a narrow but finite thickness band rather than a crack which has no thickness. And the big advantage of this is that you can then use the mechanism of fracture mechanics to work out conditions for the propagation of the band. And here's a simple example that was adapted from a calculation Rice did long ago. So here you have a band, semi-infinite band in an infinite layer. Okay, the layer has thickness h, band c h. You displace the boundaries, make them closer by an amount delta, and you want to calculate the critical energy release required to move this band ahead a unit distance. Because of the geometry, that corresponds to taking a slice of material out here, which the deformation is homogeneous, and moving it way behind the band, which the deformation is also homogeneous inside and outside the band. So the difference between those is the energy released by moving this ahead a unit distance, and you can calculate that. But if C is small compared to 1, the thickness of the band is small compared to a layer, it just reduces to the net compaction, which is here, times the stress, which you might have guessed in the first place. If you put in numbers from Kurt-Sternloff's field data, you find that this energy release rate comes out to about 40 kilojoules per meter squared. Now, that's also been measured in the lab using notched samples, and somewhat surprisingly, that turns out to be about the same value that they get for these sandstones. Why is it surprising? Because we saw that in the lab you always get crushing. Okay, in the field, particularly in Sternloff's field area, You don't get crushing. The grains move closer together. Stresses are much higher in the lab than thought to be in the field, but still these energy release rates are similar. So I don't know whether that's coincidence or saying something about band formation that I don't really understand. How am I doing on time?
You got 7 minutes.
Oh, 7 minutes, so I got plenty, okay.
Well, we lost 15 at the start.
Lost 15 at the start, so you're saying I have 20 minutes? Okay, okay. Well, I should get close to finishing then. So this is another from the work of Cheryl Temba in her thesis at SUNY Stony Brook. So these are plots of the midpoint thickness, which remember is a proxy for the inelastic compaction. And this is mostly Sternloff's data, but there's a few more on here. And the lab data is over here. If you fit a line to the field data, these are log scale. The slope of that line is almost a half. So that says this inelastic compaction goes as the square root of the length. So what's the model that gives that? Okay, it's this, I call it combined anti-crack and anti-dislocation. So it's a model in which you have a fixed amount of compaction here, maybe triggered by these localization processes that I outlined earlier. Here you have tractions resisting further compaction, and these are taken to be uniform. And again, you can kind of see what's happening here. This fixed amount of compaction is going to drive the stress here higher, essentially infinite in the anti-crack model, and this thing is going to spread. That's a problem for which you can look up the solution for the coefficient of that singularity at the crack tip. This thing is roughly 1, and you can use the relation between the critical energy release rate and the critical stress intensity factor. So this is relation due to Irwin. And you rearrange this a bit, and you find that, yeah, the compaction, which is compactive displacement here, goes as the square root of length. And this coefficient depends on the shear modulus and the critical energy release rate. So you can put in critical energy release rates from that we inferred before, typical Poisson's ratio and shear modulus, and you get this relation here. When you plot that, okay, so I should have mentioned this before. Okay, so then in this model, I forgot to mention this. So K actually goes down with length. So as this gets longer, the stress intensity at the tip of the zone gets smaller. And so you have kind of a picture like this. This is, again, a cartoon-like picture, but so you have this dislocation event, uniform compaction here. It causes the stress intensity factor to be higher than critical. So this runs out until that stress intensity factor decreases to the critical amount. So by looking at the final length of the thing, that corresponds to the critical stress intensity factor, which is what we did in the calculation. When you plot that, it agrees quite well. Okay, there are various lines on here, but the model fit is this one, the black line. So it fits quite well with the field data. The lab data is above that, but you can understand that because the band runs out of the sides of the sample before it gets before the energy release rate drops to that critical value. So it's consistent with the picture that these are above that line for the field data. Okay, so these are conclusions. Yeah, you see these pure compaction bands and shear enhanced compaction bands a lot in both field and laboratory data. This what a bifurcation framework gives predictions for the band formation that are consistent with laboratory experiments. And the compaction bands, or shear enhanced compaction bands, tend to form on the portion of this yield surface where they're typically observed. The predictions, although they're qualitatively consistent, are not really quantitatively, do not agree quantitatively well. There's a need for better constitutive data, so a lot depends on what you put in for these parameters that describe the material response. More complex load paths are useful in constraining these models. Work Joe has done recently addresses this question. A few more conclusions. This simple fracture and dislocation model, again, gives results that are consistent with this field data. This model is a bit speculative because you don't really see evidence of this uniform compactive event, or you don't know much of anything about the propagation of these bands. You see only the final state. And closer observations of what's going on at the tip of bands might be useful, although this is a hard thing to observe either in the field or the laboratory. And there are a bunch of questions still remaining here. Some of this work is a bit dated, and there's been a lot of computer simulations and additional observations in the field, but I think there's still a discrepancy between what we understand about the lab events and the field events. There hasn't really been a good microstructural model that, obviously it's going to involve cracking of these grains or breaking of the things that keep the grains together, the cemented. There has been some work of this using breakage mechanics, and I think that's been helpful. We don't understand much of anything about the configuration of these bands in the field, what controls their spacing, their orientation, and length. Another big question is probably these bands formed under saturated conditions, but the effect of the fluid on the band formation really has not been addressed. Okay, the field observations that people make are on, well, of course, they're on the surface, but the information from the geological structure is that they formed at depth, and they're typical of formations that people do inject fluid or withdraw fluid from. And yeah, again, the transition from band formation to extension hasn't really been looked at in much detail. So there's still a lot of questions about this, even though there's been a lot of work. And I think that's it. So thank you. And I'm happy to entertain questions.
Are there any questions or comments?
So I had a question that it turns out is similar to one of the, I guess, unknowns that you said in the questions
Okay.
still to be answered, and that has to do with a sort of something like the scaling in the field or the spacing of the cracks in the field.
Yes.
And I guess maybe more specifically, it seems like you modeled the process like a nucleation transition. So there's a
Right.
local thing that changes. But is there any evidence that it's more like sort of a spine, I don't know how to sort of phrase the whole thing, but a spinodal decomposition, so that it's more like a system-wide scale where you get multiple failures all at once? Or as you, at least in the lab, as you compress something, do you see one local compression band form and then another, which would suggest the nucleation is more
Well,
relevant?
in the lab, that's what you see. So
Just
you
one,
see bands that are triggered near the ends because of stress inhomogeneity. Then you get another band form, and they progress into the sample. And they have this laminar structure where there's a band, and there's relatively well, there's less compacted material between the bands. In the lab, that spacing almost certainly has something to do with the grain size, but a specific, I'm not sure there's a specific, well, and there have been some simulations which suggest that it also depends strongly on the inhomogeneity of the sample. So samples that have less homogeneous microstructure are more likely to form, well, that controls to some extent the spacing.
Okay.
Okay.
And then one more quick question has to do with, you said the predictions work well qualitatively with the lab data, but not quantitatively.
Yes.
And I'm wondering how much that might be due to the fact that you have stresses that are so high that you have crushing of the particles where that might not be taken into account in the model, and can you comment on that? Does that make sense?
Yeah. That certainly could be a factor. I mean, that is taken into account really very indirectly through this beta. So when beta is more negative, that might correspond to more crushing. But there's no microstructural model that relates, say, crushing or just moving grains together in any quantitative way to that beta. Okay, so the answer is yeah, that's probably a factor, but right now I don't know how to account for that.
It's interesting if you compare lab data with field data, the lab data is done relatively quickly and shortly.
Yes.
Whereas the field, it's been there for thousands and thousands of years. So
Yeah.
the constitutive behavior of that material could change, just a time-dependent phenomenon, which, and I know it's a very complex thing. I'm not trying to be clever about it, but is that taken into account?
No. So, yeah, there's not really much information about the time that it takes the bands to form in the field, but certainly if it's a relatively long time, this kind of constitutive model is probably inappropriate. Okay.
The reason I ask is that in the underground research lab in France, Bureau, argillite between two limestones, and the stress state, the stress state is measured in the limestones is dramatically different than in the argillite, because the argillite has a different dilatation, yield behavior.
Yeah.
So it's, okay.
Well, yeah, so that inhomogeneity is not really taken into account in these models. So, if you saw compaction bands in your case, yeah, you might be able to constrain that using the different properties of the two materials.
If my memory is correct, it looked like it was really shards and shattered rock that formed these sandstones or whatever we might call them. We're most familiar with very spherical particle size sands that we work in here. And I know that we have sent a lot of samples to the people in the west and the north who are looking at oil extraction and similar materials in Canada. Is this really just applied to where there's this almost shattered sand particles? Was it Nevada?
Well, no, in the field, I showed that slide where there are relatively unshattered and then there were shattered samples. That was from the field site in Nevada. So you see a combination, but probably in the field you see less shattering. Likely stresses were much less than in the laboratory. Laboratory, you almost always see these very crushed, shattered grains. I'm not sure that answers your question.
I was just wondering, does it really apply in something that's just a whole bunch of spheres, maybe of different sizes, but rather than blocks where some of it almost looked like you could say it was brick, you staggered the bond and everything.
Yeah, I'm not sure how to address that. These grains are more angular. Okay, so certainly you could get, you can see that level that's a stress in the grains and could lead to cracking. I'm not sure. I think a can happen in spherical grains, but I couldn't cite a specific observation of that.
Okay, one more question, and then Glenn.
Sort of following along that, it seems that your propagation model that you presented required that high stress at the tips. That
Yes.
seemed completely inconsistent with the field scale observations where there was no crushing.
Oh, ahead of the
that-
tip.
But
Yeah.
as it propagated over long distances like that, you didn't see the crushing. So it seems like you explained it in one case, but not the other.
You mean why there was no crushing in the field sample?
Yes, and still propagated.
Yeah, so you're saying that you had these high stresses so at the tips as the thing propagates, so why don't you get crushing?
What I'm suggesting is that your propagation model doesn't explain what we see in the field.
Yeah, I'll accept that. I mean, it's a very simple model. What it does explain is one of the few quantitative things that are measured in the field. Yeah, so yeah, certainly it doesn't. I mean, that's a good point. Why don't you get crushing? I mean, I guess I could answer that as that the model takes an extreme idealization where you get essentially infinite stresses at the tip, but a more nuanced model, which is say this ellipsoidal model that I looked at, you get stresses which are, of course, not infinite, and they're higher than the surrounding material, but possibly not high enough to crush the material. That's kind of a Weasley answer, but yeah, that's the best I can do with it. I got a lot of blowback on that model from Attila Iden, who's been a friend of mine for a long time, and if he doesn't criticize me, I'm worried because that means we've fallen out of friendship. But he's a geologist, and yeah, I got a lot of blowback from him. It's a very simple model. It does explain that one quantitative fit, but yeah, I agree that there's a lot of things that might be improved about it.
Okay, thank you, John. I'd like to end by recognizing you as the 2017 Vardalakis Lecturer. Please join me in thanking John.
Okay, thank you. I'm very pleased to do it. Yeah.